An honor to have Jonathan Hurst with us today. It's Jonathan. He's a Chief Technology Officer and co-founder of Agility Robotics. He's also working as an associate professor at Oregon State University. And in today's talk, he's going to tell us about his experiences working at the Agility Robotics, and about the use cases. So the floor is yours.
Excellent.
Jonathan.
Thank you very much. And thank you for your work getting this all set up. No problem being the guinea pig. Hopefully it'll work pretty well for everyone. Thanks. So I'm going to talk today about our robots and about getting them out into the field and into the real world. The perspective that I'm going to bring is maybe a little bit less technical than most ICRA talks, because this has been my world for the past year, where being able to get a machine out into the world requires a business case, it requires customers, it requires a use case, something where we can start to make some profit off of it and some money in order to pour that back into continued development and get this flywheel going, where the applications really drive the development and it just is able to move forward. And so I'll talk a little bit about certainly robots in human spaces, which is our whole goal. But let's see here, there we go. The function of this talk, or the format of this talk, is to give you a little bit of the business overview and the context of what we're trying to do, of what we're doing as a company in order to justify our existence, in order to justify our growth and our technical efforts. I'll talk a little bit about the science core, and certainly anybody who's heard a talk from me before will be familiar with it. It's not going to be new, the science hasn't changed. But I want to make sure there's a bit of just a bit of a foundation there for how we view the world technically. And then the technology, which is about implementing the science into the machines. And like I said, I'm happy to have questions throughout. I don't have any good way of seeing if someone's raising their hand or something like that. So I hope that Dimitrios or whoever, just unmute yourself and ask that question. If it gets to be too much, we can change it a little bit, but I doubt it will. So pop in if you've got a question and we can talk about it. And then there will be plenty of time for questions afterwards. And I'm happy to talk about our robots or more technical directions or whatever you like beyond the scope of this talk. Okay, so the business context and business overview. We're looking at this use case of manual labor, which is standard for automation. I mean, a lot of manual labor in manufacturing and all kinds of places and in warehouses has been automated with very special purpose, bolt down kinds of robots. But there's still an awful lot of jobs that are really basic manual labor. And these are the kinds of jobs where people are already treated like a robot. It's a kind of thing where you pick up a box, you scan it, then a little light goes on one of two locations, and you set the box in that other location. And that's all you do all day long, every day. And your performance is exactly tracked, and there's no creativity and there's no decision making. These are the kinds of jobs where really people are more useful in other places, using robots and other tools to leverage their capabilities. And looking at the market size, we've got a video out with Ford Motor Company about doing this kind of last mile package delivery. And that's a really valuable thing. You imagine how many packages are coming to front doorsteps on a daily basis. But it's actually dwarfed by all the manual labor that's done inside of these warehouses. This plot shows, or this bar graph shows something like 3 million jobs in 2019 doing these things. It's grown rapidly since then. And there's high turnover. There's a very high injury rate, very high death rate, which is really surprising to me that these kinds of jobs are this dangerous and still it's changing rapidly. So it's ripe for automation. There is going to be automation. The question is how, who's going to do it, how is it going to be done? A lot of these warehouses are built around humans and built around jobs that are for humans. And that's where Digit comes in. This robot is built for a human-centered world. Now, this is a reasonably, hopefully familiar argument for humanoid robots. Why do you build a humanoid robot? It's because we've designed and built our entire environment around ourselves. all of the sidewalks and the doorways and stairs and a lot of the tasks, and physical interaction tasks and manual tasks that people do have been designed around our form factor. And so having a robot that matches our form factor gives it huge versatility and the ability to do a wide range of different jobs and do it in our spaces. But here's a very important distinction. We have not designed and built Digit trying to copy the form factor of a person. Instead, what we've looked at are the specific jobs and tasks and performance that we want to achieve, and then have really aimed from a ground up, first principles kind of approach to getting the performance that we're trying to achieve. So for example, we want to handle unstructured indoor-outdoor spaces. That's rough terrain, it's stairs, it's walking, it's accelerating up to a light jog, things like that. Well, this leg configuration is not exactly humanoid. It looks a little bit like a bird. And that's because, that's coincidence, you know, we didn't design it to look like a bird, but it's that we started with something that looked nothing morphologically like an animal. And we worked our way up as we worked and understood the engineering approach to create the forces on the ground, to create the performance that we wanted. Things like very, very transparent transmissions, so we can do very good force and torque control at the joints in the legs. Even the form factor of the arms, they're more like a set of, well, bilaterally symmetrical tails, for lack of a better word, right? It's to balance the robot, to catch the robot when it falls, to reorient the body, to get up off the ground. These were a lot of the engineering direction of those arms before it was manipulation. So it's designed for human performance in terms of force-sensitive interaction with the world and physical interaction. And that really has been the approach from the very beginning. Our goal is this: jobs become software. You know, the capabilities are there in order to do the different skills you might call, that you might build up to create a particular job. So pick up a box, you know, identifying that box, reaching over by manual manipulation, pick it up. That is one skill. Being able to walk around anywhere you want to go, up and down stairs, outdoors, in and out of the truck, that's another important skill. You know, self-charging, you know, I don't know, some human interaction sorts of things. And you put all that together and you get robots that are going into a back room and bringing out a package for counter service. You get robots that are doing that last 50 feet delivery from an autonomous vehicle. You get robots that are going outside and doing yard inspection. You know, these big logistics companies, they don't know necessarily which trucks are there and which ones are out and where they are, but they have people going out and with scanners tracking the barcodes on all these vehicles. Well, a robot can do that. And this is in a human environment, and this is with people monitoring and supervising these machines. And maybe there's one robot doing all these different jobs at a different time of the day, where that's just a software difference, you know, or it's 10 different robots doing the same job. Now, the first jobs we do, especially the first ones, are going to be the easiest, the dullest, the dirtiest, you know, the most dangerous kinds of boring jobs. And this tote stacking job is an example of that. You wouldn't think that this is dangerous, but it actually is. This is one of the biggest sources of injuries in the warehouses because these totes get damaged and maybe the sharp edges of the plastic are exposed and people cut themselves a lot. Plus, there's a lot of just things on feet and back problems and things like that. But it's a job that's been very hard to automate because maybe only it needs to be done for a couple hours in one location and another hour in another location. But it's a huge bottleneck for some of these logistics companies. So we know exactly what the KPIs are, the key performance indicators. We know exactly what the job entails. We know that there's going to be a tote coming down the line. You want to pick up the tote, stack it in a pile 8 high, and then a little mobile robot is going to wheel that stack of totes away and to the beginning of the line where they can fill it with things and do all the pick and place stuff. So we're really looking for those kinds of jobs and working with customers to find those kinds of jobs for the very first entry-level things that Digit will be able to do. We can develop those behaviors in test and simulation because they're so well defined, then start doing test deployments in our own laboratory, and then start deploying them at scale with customers. Now, you're probably familiar with a lot of this competition, but I just want to lay out this structure that the single purpose automation is really important. It's going to be a solution that will always exist in the constellation of solutions. But you know, we're not competing with that. We're not trying to do a single purpose specialized machine. We're aiming for this much more versatile kind of automation in human spaces. The other thing about a lot of this automation is people can't interact with or be in that space. It has to be completely 100% reliable automation. Cobots, of course, people can be around, but it's still an environment engineered around the robots and they're bolted down. And then there's like Fetch Robotics and others that are doing the mobile robots. I think the autonomous forklifts and things like that fit in this category, but still a warehouse needs to be designed and built around these solutions. They're mobile, they go around, but you need the just right flat floors, you need the width of the aisles, you need a lot in order to integrate those robots. It's only very recently that any companies or organizations have been able to build machines that can go where people go. And that's Boston Dynamics, it's Agility Robotics, it's others who are starting to do some really cool things. And this towards this holy grail of low cost, adaptable, robust automation in human spaces. That's the dream. I hope that by the time I retire, past that, by the time I really need help around the house, I hope it's an Agility Robotics robot that comes in and is helping me around the home as I'm 90 years old. Okay, so that's the business overview, that's the context, that's what we're aiming for and what we're trying to achieve. Now I'm going to go through just the basic science core to make sure that we're, you understand how we look at this problem from a technical point of view. And I start with the foundations of locomotion, the real basics of physics, okay? This is just the physical hardware, the lowest level of the physical interaction with the environment, which is something that is often overlooked in robotics. But with legged locomotion, it cannot be overlooked. There's just regular impacts with the ground. It's a very challenging physical interaction task. So look at this video of the fish swimming. You know, it's actually a dead fish and it's swimming upstream against this little rock basically right here, and the flow is going across the stream this way. It's just the interaction of the fluid dynamics with the body of the fish. Of course, it needs control if it's going to swim anywhere in the river, but a lot of this is just done with that physical interaction. Same with this is, you know, a long ago collaboration. A guinea fowl that's just totally surprised by this you know, tissue paper stretched across the ground. It didn't know that that was going to be a hole, completely unexpected. And it just keeps going. Now, this is not a reflex. This is not a planned interaction with the world. This is the dynamics being robust. That is the lowest layer that we need to be able to achieve and that we bake into the robots. Now, we know that spring mass dynamics, a very simple reduced order model, reproduce walking and running. In fact, spring mass models of quadrupeds and others reproduce every known locomotion gait that nature has seen and then some. That's amazing. It's a really, really simple model. There's something to this. Now, of course, this doesn't capture everything. This is a model that captures some of the basic physics that we want to achieve, and it captures, you know, gives us a high-level understanding of what's going on, but of course not how to control it. It's just related to the some of the rules that we need to play by, basically, are some of the same rules that spring mass dynamics play by. Now, playing by those rules and adding some simple look-ahead planning to the spring mass model, you can get pretty nice behaviors. This is just a Monte Carlo two-step look-ahead. My student, Patrick Clary, who's now working at Agility Robotics, put this together. Of course, it's planar. Of course, it's a fairly simple model. This is doing simple actuation in the mid stance and also choosing footstep location. But it's not choosing a trajectory. It's not choosing specific foot placements. It's got sort of locations where it can go, and then it's trying to plan through those dynamics. And the only reason that this planner works is because it's working on top of these underlying dynamics. This planner wouldn't work without this model. It's very much integrated. Okay, there's the science core, familiar to many. Now a little bit about our technology, okay? I talked about the background of trying to create robots that morphologically look nothing like an animal, like Atreus here. It's this 4-bar linkage, low inertia, basically a spring mass model. And we found some issues with antagonistic work, where one motor was always acting like a brake, and the other motor had to do twice as much work as necessary in order to get around in the world. So it's very inefficient, very lucky that we had extremely powerful motors on it, but we were able to demonstrate and show the basic science. This Cassie leg configuration then is not quite as directly simple and symmetrical as this 4-bar linkage for controls, but it does capture and can exhibit the same spring mass dynamics while eliminating that antagonistic work problem. We also add a couple degrees of freedom. So this robot has gone out to a number of the top universities in the world for people to really demonstrate good control behaviors. And that's a useful starting point. You don't have to build your own robot. Now, since then, Agility Robotics has been working on the upper body and getting up to the digit. Internally, we call it V3, but just shipping now the very first product, the digit robot. Now, I talked about the passive dynamics. This is down here at the dynamics foundation. And I like to think about it maybe as a control hierarchy, which is layered by control rate and perhaps by information content. So all of the information that exists down here at the physical interaction with the world, the world model, the interactions with the ground, you know, all those low-level forces, that information doesn't exist way up here at the user input, the high-level intent, the waypoints. It doesn't even exist here at some continuously updated plan. But it's necessary to have this happen at infinite kilohertz, you know, or I don't know, 4,000 kilohertz, hertz, something like that. So you can actually handle impacts and things that happen on the scale of the dynamics of the robot. Then you've got some maybe 2 kilohertz controllers, but you know, there's inertias in the motors, there's all kinds of passive dynamics and things in the physical device that mean making your controller much faster, react quicker, doesn't really help you. You're still trapped behind the dynamics foundation of your robot. Or enabled by. You kind of look at it two ways, and it depends on the piece of hardware and whether your real-time control is integrated well with your dynamics foundation or whether it isn't. And then, of course, on top of that, continuously updated plans. Now, this might be a really simple reduced order model compared to the full order model of the robot. So long as you update it pretty quickly and your model is your plan being sent down the line is pretty close to what you really need to be doing, but you're updating it all the time, tends to be good enough. And then, of course, the high-level user input. Now, here's just a representation showing our simple reduced order model. Start with that spring mass behavior that we want. Maybe this is even the template for our control, okay? And gradually working up and adding bits of physics and inertias and things like that to get to the physical device that actually implements it in, you know, as close as we can reasonably get. So when you engineer, that was the key behind Atreus, is engineering the hardware dynamics and integrating that with the control to try and get the behavior that you want. And then we see, of course, Atreus running over all kinds of terrain and this being comparable to what the bird is doing. So really the point of this is it's the same physics, it's the same performance as something that we see from animals. In this video, it is only the low-level dynamics that we're showing right here. There's really no planning, there's no high-level intent other than just a velocity, something like that. So understanding the physics is more important than copying the morphology. And okay, so this is a little bit more recent. We have Cassie, where again, I said that the dynamics are a little more complicated than with Atreus. Atreus, our controls could be very heuristic based because we could make a lot of assumptions about, you know, exactly applying equal and opposite torque and getting a force in the leg length direction, things like that. But here with Cassie, the inertias of all the devices and where the springs act start to get a little more complex for the control. That is a necessary thing, though. The robots of the future are not going to be these incredibly dynamically simple devices. It's going to be a lot more complicated. We're going to need to use tools like machine learning in order to really understand the dynamics and really control these machines. So with Cassie, we're able to basically walk around, stand, do some fairly slow behaviors with engineered controllers, but it isn't without, we weren't able to run until we started using some structured machine learning, where we kind of give it some of the information that we know about the robot and how it should behave, and then explore a little bit with the learned policies. And so here it is running on the treadmill with a nice dynamic behavior. And I think we'll get a slow-mo here and you'll see that it really is starting to look a little bit like a biological behavior, like the running behavior. You know, it's really bouncing the way you would expect from an animal. And this is really not a stereotypical robotic behavior. Although robots have done this before, this is not a first. I think this may be the first bipedal balanced robot that is using a learned policy. But boy, there's a long ways to go. This particular controller certainly works. It's very brittle. You can see it's kind of wandering around on the treadmill a bit. You know, we had trouble controlling its speed. It's going forward and back. Its control in the yaw is not great. When we take this controller outside, we got it to run on nice flat ground like on the football field. But if we're running on pavement, the friction between the feet and the ground wasn't enough, and the robot would twist sideways and fall. Also, the slight crown in the road, where there's a slight sideways tilt to the road, is very sensitive to that. So there's a long ways to go with figuring out how to do good learned policies to make this robust outside, in addition to just getting these behaviors in the first place. All right. How do I, there we go. So here's Digit now, where we've got some of those low-level dynamics, but adding some of the, this is all planned. Like there's perception, although the robot, well, in this video, the robot doesn't use any of its perception right now. We have cameras underneath the robot that can show ground plane surface, because you can't just walk around like this on stairs. You do need to plan your behavior. So here we do tell the robot where the stairs are, and it's planning its way up, but you can see it stubs its toe a couple times. Those dynamics are still really important, low-level dynamics. Oh, look at that. We try not to be too mean to our robots. But there's no better way to show the disturbance of, you know, a great big step that it can take to be robust. This last video that it's going to show, it steps up onto a box. It does know where that box is, but it wasn't planning to take a step. It had to take a quick step onto that box right here in order to balance itself. All right, now we're adding in some high-level planning. It starts to look a lot more boring, a lot less dynamic, because we don't, you know, we're not testing that part of it here. What we're doing is giving it high-level commands of stack these boxes from this location over to that location. It's basically a script of, you know, walk to this location, pick up box, walk to that location, set box down. And through that hierarchy is able to handle it. Now, what I'd like to do soon, and I don't have for this presentation, but would like to do soon, is this same behavior, but all kinds of, you know, an obstacle course in the middle, trying to achieve something where it's picking up that box, but maybe the box has a string attached to it and it's confusing the robot a little bit. It's walking over foam and maybe a couple stairs on the way. You know, that starts to demonstrate that control hierarchy of the high level intention combined with all of the dynamics that you do. Also, obviously, we cheated here on the vision. We have the fiducials on there, so we don't have to do the whole vision layer stack of identifying where a cardboard box is. All right, I think that's enough. I'll move forward here. Digit is in production and shipping, so that's new and different. You know, so it's a humanoid robot that you can buy. And here's a video from just a couple days ago. We've got our robots now. This is sort of the customer burn-in. We want to make sure that these robots are functional and aren't, you know, a little wire isn't loose or something like that internally. So we walk these robots around for a while before we ship them to customers. The robot in the middle that's untethered is being controlled by one of the operators. The other two robots that are walking back and forth on the tethers, they're just doing kind of a waypoint pattern of back and forth and around. Now the covers are off the robot, so you just see the flat shell of the aluminum in the center and the context camera in the middle. You can see some of the Intel RealSense cameras on the top and bottom of the torso there, plus the LiDAR at the top. But then look at photographs in the future for any of the shells in the operation. I don't know why they had the shells off the robots for this. I think they should have had them on there. Oh, and here's, I guess at the beginning you saw the robot get up, but here's the robot's sort of get down and lay down procedure, and then get back up. Up we go. All right. So I think this is clear. Bipedal robots, they're ready to work in human spaces. We're about there. It's so close. I know that in the not distant future, there's going to be thousands and thousands of these robots in our homes, our workplaces, outside delivering packages. I think legged robots are going to be, more common than vehicles and wheeled vehicles and cars on the roads. They're just so useful. There's so many places for them to be useful. So with that, I'll finish my talk. Thank you for attending, and I am happy to have a conversation and answer a bunch of questions.
All right, thanks a lot, Jonathan. This was super interesting. Thank you very much. I got a couple of questions, and I noted also some things on my side. Okay, so the first question is from Luca. It says, how leg design and walking gait control has changed transitioning from Cassie to Digit, from legs only to full body robot?
Okay, that's a good question. A couple of answers. One I'll say is that although the configuration is the same of the legs, because physics hasn't changed, and it's a really good configuration for having low unsprung mass, low impact with the ground, and having that physical compliance in the springs that you can see in the picture on the right there. It's the flat black bar is a fiberglass spring. There's another one underneath sort of the shin shell. So that's still the same, but every single part has changed from Cassie. There's a lot more sensing on board and things like that for convenience. Cassie, for example, has a whole calibration procedure every time you turn it on because there's only a single encoder on every joint. Digit has dual encoders in all the joints. So you turn it on and it's just, that's all you need to do is turn it on and it's ready to go and it's calibrated and knows where it is in the world. So a lot of engineering went into making that improved. There's also 2 degrees of freedom at the ankle now. One of the things that we found, again, this has been a first principles approach all the way. We start with the simplest thing we can do, looking at something like Atrius, and we only add a feature if we find that there's a clear deficiency that we need to fix and improve. Well, one of the deficiencies, let's see if I can back up a few slides. Was it in this video? No, I think it was here. Watch Digit V2 climbing up the stairs. I thought it was in this video. Maybe not. I showed the video of Digit climbing up the stairs, and that was a Digit V1, an earlier version of the robot. And when it did that, boy, does anybody remember where that was? Shoot. Not here. Anyway, when it was going up the stairs, you have to go fast because it's like walking on an ice skate. And as soon as you're standing on one foot, you're falling in one direction or another. And there's no way to move your center of pressure at all or to change any of that. So you're just like with the early Atrius robot, the sole piece of control is foot placement. And you only get one chance at foot placement. And your foot placement is going to be off a little bit. It's not going to be exactly where you want it, in part just because sensors are noisy, late, and wrong, and you can't model the environment very accurately. So having a little bit of control over foot pressure is really valuable, and that's what we needed to do. That was one of the design changes with Digit here, is adding these larger feet that allow you to change the center of pressure a bit while not affecting the rest of the dynamics too much. Now, you were asking specifically about the whole body control, and there's no question that it's changed a lot. When the robot is moving around, it uses the arms. It's not puppeteered. You know, when the arms swing and things like that, and it looks somewhat natural, well, that's only because it's capturing the same physics that a person might. When the robot is twisting or moving, it swings its arms as a key portion of the control. And there's some challenge in identifying when you're touching something and what it's going to be, like how heavy is that box, and then estimating the weight of the box, and then using that as your new inertia as you're balancing around. That's still in progress, and it's something that we've done some demos for, but it's not really integrated well yet. So yes, the whole body control is a whole new ground up refactor and change from anything we did with Cassie before we had the digit robot. Did that answer the question? I think I got maybe two.
Right. Yes, I think you got it. I mean, I just want just a little bit to elaborate before we go to the rest of questions. We have a bunch of. I remember a couple of years ago, I guess, in one of your talks, you said that you have studied animals on energy efficiency, etc., etc. So did this change in digit compared to Cassie, or you went in a different direction that we are not as much bio-inspired as before?
Okay, that's a good question, and I will say that sort of touches a sensitive point for me in talking with a bunch of the controls team and working on this, right? Part of this has to do with what's our application right now, and our application is carrying these boxes around a warehouse, and we have a pretty small team. And so the physical capability of Digit is absolutely there to do all of these highly dynamic behaviors. And we've done a few demo pieces where the robot is absolutely following those dynamic behaviors. But in some of these videos, it's not really that dynamic. Well, I guess you could argue, what do you mean by dynamic, right? It's not jumping up and down in these videos. It's not running in these videos. But what business use case is there to run? So while it can do that, and while we will do that, it's not a today problem that the software team has been really focusing on. They've been focusing on a lot of other things.
All right. Okay. So next question is from Hendrik Kolvenbach. I guess it's about the cost of these robots.
Sure. We're selling these robots for $250,000 right now. And we certainly, when we're working with companies, then partnering with them, the vision is as we volume up and as we continue to do design revisions, we can get the cost down, push the cost down, push the cost down. In volumes of, say, 1,000 robots, when we start working with one of the big companies, just volume purchases of the robot as it is now can cut the cost down to $150,000. And if we have the opportunity as a company to be successful and really continue to refine and revise these, we are going to be able to get that cost down much, much lower than that. I think everybody probably saw the spot robots are for sale for, I think, about $75,000 right now. I'm sure that in volume, we can be doing that for a full humanoid like this.
All right. Sorry, I'm muting also some people that by accident they unmute. All right, that's great. Thank you. Another question from Joao Ramos. How much difference does the two-door Funko make on robustness and ease of control?
It has a lot of effects. So obviously you can now balance on one foot, and we have some nice video, where you can say, when we were doing initial testing, we had a robot that one of the arms was malfunctioning, so they'd pulled that arm off, and one of the other legs had a problem, so they pulled that leg off. But the prototype team was still able to be working on the robot with one leg and one arm, balance on one foot, and move it all around and be checking out the whole rest of the system. You can't do that without a 2-degree of freedom ankle. Being able to go upstairs, you don't have to hurry. You can pause, slow down, and stop if you want to, because you can change your center of pressure around. So some of those things, it's a huge benefit to the point of really being a necessity. If you're standing on your 2 feet and you're moving boxes around and you need to be taking steps and planning where you're going, it's really important. It adds a bit of inertia down low to the leg. So if we're trying to have a robot that runs, like you saw the video of Cassie running on the treadmill, it changes things a little bit. And now we really need to start incorporating a change in how the foot interacts with the ground. It's no longer like with Atreus and with the early Cassie. I would say we didn't know how feet worked, okay? Basically, we knew what a spring mass model is and how that works, and that assumes a massless leg, and we can create all these behaviors that way. But understanding how a foot works and how that interacts with a lot of inertia in a leg, like a human leg, it's a lot more complicated. And we were sort of avoiding that problem for some time. We're beginning to address that problem now and have some really good success with that. And so what I anticipate seeing in the near future with Digit is being able to do some of the more dynamic behaviors with a heel strike, basically, with managing with a lower inertia way out at the very end effector, sort of like a hoof or running on your toes, that kind of thing. Having that manage that initial impact so that the unsprung mass of the leg and the 2 degree of freedom motors and everything else come to a rest on the ground without that harsh impact, but only in the first 10% of stance phase it's handled. Then the whole rest of the mid stance phase, you have that really transparent transmission in your legs that's handling the very large forces between the ground and the body. So it sort of becomes like a 2-stage impact almost, where you've got the lower inertia, smaller actuators out at the distal end catching the leg mass, and then the leg mass, once that's matched to the ground speed, is now controlling all of the forces applied on the body. So I think we now have an understanding of how feet work, at least, again, not so much morphologically, but the principle of it and how we want to implement it on the machine, and have some of that functioning on the test plates and on a test robot right now. So it changes things a little bit. There's pros and cons. We can't treat the robot as simply as we did before with just assuming the leg is massless, because it's not anymore.
All right. On this aspect, on the leg design, actually, Max Roa is asking if you could apply the same controller to a robot that needs forward configuration.
It depends, right? So the morphology doesn't directly matter. If we had a forward knee or a, 6-jointed leg or whatever, it is less important, much less important than what are the dynamics when it impacts with the ground. And are you able to, say, send a torque command and get that torque command? So the things that matter about the leg are, in this case, minimizing that mass out at the end effector, minimizing the reflected inertia of these actuators, which is pretty high, or finding a way around it by, say, adding those springs to handle that impact. But then you have to control through that spring. So it really has to be just the right spring integrated with the controls in just the right way. If you add a spring, things just get wiggly and hard to control if you haven't really dialed it in and integrated it well with part of the controls. And then the other thing that's really critical here is if you command 10 newtons, are you going to get 10 newtons? So think of it this way. Let's ignore closed loop sensors for the moment. So ignore like load cells or series elastic actuators and say, I'm just going to have near direct drive, or in this case, a very efficient transmission. Our transmissions in the thigh and the hip are, according to our dynamometer, 94% efficient. That means if you apply what you think is 10 newtons, or 10 Newton meters if it's torque, okay, you're getting 9.4 Newton meters if you're driving it forward in one direction, or if it's being back driven against what you think is 10, then it's what, 10.6 or ish, higher than 10 Newton meters. And you've got this range where you don't necessarily know in a very short time scale if you're driving forward or if you're back driving. You don't know that until your control cycle has gone through. So you don't know in a very short time scale, about a 10% error in the amount of torque that you're applying. It's either 9.4 or it's 10.6 or something like that. So getting the efficient, but if you had a 70% efficient transmission like a harmonic drive, then it's terrible. It's like a plus or minus 30% error in the torque that you're applying. So having those really transparent transmissions that allow you to apply a torque and get that torque or close enough while you're driving forward or driving back, that's critical for being able to control something that is physically interacting with the world. It's very much not a position control kind of behavior. The positions and the trajectories that you see are just a result or just a symptom of the dynamics that you're trying to create. And to create those dynamics, you really have to think about all of the inertias, all of the reflected inertias of the actuators, the frictions and stuff in the transmissions, and the physical compliance in the system, and have that be part of your control system, part of your design of the behavior.
All right. On this, sorry, we have like 6 more questions. Are you available to?
Sure.
All right, perfect.
Yes,
So,
that's just fine.
all right, okay. So Soon Guan is asking if in the machine learning approach with Cassie, if you have observed the center of mass trajectory to see if it exhibits behaviors like a sleep model.
You know, we haven't put a motion tracker on it, and we haven't run across a force plate. But, you know, just watch it in the slow motion, and you tell me, is this bouncing up and down the way you would expect from an animal? I think so. I believe so. I think it's pretty clear from this that you're getting, the legs are compressing at exactly the right time. You know, the force profile on this looks pretty good. If we look at the forces that we're applying, it looks pretty good, like an animal, or like you would expect from the spring mass behavior. And then the center of mass motion, just watching the video. Again, not collecting data, just watching the video is capturing it. So I think this is a good, I don't know, what would you call it? An example, a case study, not even that, an example of being able to do this successfully. But what it is not is a finished, really functional policy that's robust outdoors with a lot of data captured that says this is what animals are doing. I think we're capturing a lot of the important features that we see from animals, but again, there's an awful lot of progress yet to be made here.
All right. On this aspect, I'm not sure if you can add something, but Marco Camuri is asking, in what did machine learning make the biggest impact to achieve animal level capabilities on Cassie? And what was the hardest thing to model on Cassie that required real machine learning to model it better?
Okay, I'm going to answer the first question first, and I'm going to forget what the second question is, so please remind
I
me.
will
Okay,
repeat
the first part of the question was, sorry, repeat that for
me.
So
the first part was, in what did machine learning make the biggest impact to achieve animal level capabilities on Cassie?
It's all the corners, right? So there's this reduced order model that we can control because we understand the physics of it. We know that the basic features of the physics of the reduced order model are also true for the robot, but it's really only 70% close. There's a bunch of mismatch, right? There's all kinds of inertias in this system that aren't modeled by the reduced order model, and there's all kinds of other things. With Cassie in particular, the inertia of that body is very low. And so when you swing the leg forward, there's not a lot to react against. The body can pitch around a whole lot. And especially in the yaw direction, I'm learning that for bipeds in particular, yaw is a very difficult control authority to have. It relies on friction of the ground on a relatively small foot, but you're swinging big inertias around. And if you think about all the different kinds of animals out there that are bipeds, almost all of them have some additional way to get control authority, a big tail, or in the case of humans, arms that are really important to pump your arms when you're running and things. Think of the birds, the ground running birds, like an ostrich. They use their wings a lot, and especially when they're turning. If you watch an ostrich, any videos of an ostrich, and when they're turning, they stick their wing out in order to catch the air in order to be able to turn. So that's something that I don't think was obvious to us as we were building Cassie and as we were starting to do the controls. It became much more obvious as we tried to get the speed up, that one of the main modes of failure is the robot twists sideways, and we don't have enough friction with the ground to deal with that. Now in this video, I don't know if it'll be obvious, but the leg kind of swings out and lands with the toe pointing outward, kind of like duck walking, and then twists that toe so the toe is pointing inward throughout that stance phase. And that kind of coupling, that kind of sort of twisting behavior that the feet are doing is entirely learned. You know, that's one of the corners of the dynamics. That's something that we can't easily engineer into the system. It was really clear on the right foot. It's landing with the toe pointing out, twisting that toe straight inwards as it runs in order to control the yaw a little bit. That's probably why this was so sensitive to the ground friction terms when we ran on pavement and it didn't work so well. So basically exploring the corners. If we're using our reduced order models and our engineered policy, we're not getting anywhere near the performance envelope of what the robot can actually do. We're just getting what the robot can sort of, where the overlap of the stability of our reduced order model overlaps with the stability of what the robot itself dynamics can do, treating all of the mismatch between the reduced order model and the robot dynamics as error or disturbance, whereas a learned policy can actually make use of the robot dynamics appropriately. Of course, like I said, lots of challenges. Not there's lots and lots and lots of work to be done here.
All right. Okay. I think this answers also his second question of what was the hardest thing to model that needed really the machine learning.
I had something specific to say on that though. So in my opinion, the question about what to model is not about trying to model it better. It's about building a system that doesn't really care what the model is. So in this example of Atreus, we don't have a model for that platform in front of it. The robot doesn't even know that that's there. It is just following the spring mass behavior, and it is inherently stable at a low level. We had a very, very good correlation between the behaviors that we observed on the Atreus robot and the simulated machine, even though we didn't have a very good simulation. In the simulation, the foot might penetrate through the ground and then slip sideways a bit throughout the entire stance. But in the real world, that's going to happen too. If you step in mud, you know, when are you on the ground? Is it when, you know, the first point of contact between the foot and the surface of maybe the water on the top? Or is it when you're applying full force of the robot's weight down into the ground? I mean, obviously it's a transition in between them. And so that building a dynamical system that is totally robust to those sorts of uncertainties of contact and impact means that you're also robust to those sorts of modeling noise that happen in simulation. And that, I think, is the most important part about having this sim to real transition. It's the dynamics of the system more than it is really, really good simulation fidelity, in my opinion.
All right, thank you. Let me take you a little bit back to the business model. So one question from Nathan Boyd is, what is the production rate of Digit for you, roughly? If I recall correctly, Boston Dynamics is currently doing a couple dozen spot minis every month. So they're curious of how extensive the manufacture to testing is for Digit.
We are able to make about 3 digits a month right now. We're a much smaller company than Boston Dynamics, much smaller. You know, we've existed for about 4 years. We have about 30 employees. We've raised, as a company, around $9 million total. And so that, along with the sales of the Cassie robots and the sales of the Digit robots, have kept us operating to this point. But that's, you know, at least an order of magnitude or more. You know, Boston Dynamics, they've existed for 30 some years and have, you know, really used a lot of funding to get to this point where they are now releasing their very first product. So very different organizations, very different stage of organization. We're a lot earlier in the process.
All right. On this, I guess we have another question on, you know, if it is, it says that, you know, you did 10 years of research before really going to the company. And, you know, if you think that it is still possible to build a company that manufactures robots for somebody that wants to do it now. So it's
I'll say, even for us, you know, this is was never going to be easy, but it's always been that way. So I don't know. So going back through the history, okay, I'll give you the example with Mabel. I was a Ph.D. student. I had a cool like actuator that I had made on the benchtop, and I desperately wanted to design and build this biped robot. And I happened to meet Jesse Grizzle. He saw what I had built. He happened to have a grant. He wanted to do controls research on bipedal locomotion. And, you know, it turns out you can't go out and buy a biped, right? He took a massive risk and worked with me, and had the patience and funded the parts and pieces of this robot build while I was a graduate student. I was funded through other NSF funds. So that's a massive piece of luck and a huge long shot that came through in order to build a piece of hardware. Very difficult to fund and build hardware in any sort of academic field, but you know, we were so fortunate it worked out and it was good for both of us. Atreus is a similar thing. It was a close thing. It's very difficult to fund and build hardware. You know, NSF doesn't like to fund those sorts of things. This was on a DARPA project that just happened to be a good fit for it, the DARPA Robotics Challenge and the M3 program. And someone really went out on a limb to fund us to do this. And even so, we were so close to failure, where we weren't quite there. We had a robot, but it wasn't walking. It was on a boom. It wasn't doing what we wanted it to do. And we were just about at the end of our funding and getting close to the deadline. And, you know, got a little bit of extra money right at the end and managed to pull it through and have this thing at the DRC, walking and running outside. Everything came into place so fast right at the end, but it almost missed. Similarly with a startup company, very, very difficult to do a startup company for hardware. Everybody looks at this and says, ooh, hardware, you know, usually people develop hardware, put a lot of money into it, and then it doesn't work. It's very capital intensive. You know, how is this a venture-backed company? How are you going to scale your hardware the way a software company might scale? The scaling costs are very different for hardware compared to software. So every step along the way, it has been an unlikely challenge, basically, to get to the point of starting a hardware company doing legged robots. So I don't think anything has changed today. I'm kind of, I don't know, in awe of what it is. How did Mark Rabert manage to pull in so many millions of dollars in order to keep that organization going? Now that I've been trying to do the same, it's just amazing. It's amazing. And it's very difficult to reproduce that. So in thinking about starting a company, the question is, what are you trying to achieve? Me personally, I'm trying to find any possible way to get these robots out in the world, this kind of legged machine, into the world, doing useful things, working in human environments, you know, through academia, through a business, through whatever business model. I don't care what the business model is, as long as these robots are doing useful things. That is a terrible way to start a business. The way you start a business is you find a need that a customer has that you think you can solve, and then you focus on that customer. You focus on the range of customers. You make sure you've got a big market that you're going to be able to address. And then whatever technology or whatever application you need to do in order to solve that problem, using the tools that you may uniquely have or the technology you may uniquely have, that's how you have to do that. So even now, you know, to start a company, the hardware, it should not be this complicated. It should be much more straightforward, so that it's that's not your main challenge. There are many layers of risk, so you're taking business risk, technical risk, you know, organizational risk. Can you build an organization that can execute well and lead it well? And a startup company is all about trying to reduce that risk as much as possible, so that an investor looks at this and says, well, this is a slam dunk. All you need is some money in order to scale your organization, and the business plan is clear, and the total addressable market is huge, and we totally believe the technology is going to work, and you know, this is going to be a slam dunk. That's when they really start writing checks. You know, we've been working very, very hard to keep this company moving forward and really producing these machines and getting into our customers' hands. So working very hard on use cases with 4 major industrial customers and getting the robots into their warehouses. Yeah, I don't know what else to say.
Okay.
It hasn't been easy for Boston Dynamics either.
Yeah, I know. All right. So on this topic of the business, actually on the application side, so do you see, it's a question from Ivan Simoes, if you see any other applications in the near future except warehouses work?
See, the near future is the real kicker, right? Far future, all kinds of things. Near future is the real kicker. And so really looking for applications that look kind of like, you know, where I guess was that tote stacking thing. This should be something we can do. I think another one I'm kind of excited about actually is this we've been talking with Avatar Inn, and they're a spin out of All Nippon Airlines, ANA. And their thesis is that you know, people more and more are going to be doing what we're doing right now, which is this remote interaction. But right now, it's just information, it's just data. People are going to want to log in and be able to go places and physically interact. And so they're really working on this avatar module. That's they're going to have this service where you can log in with your VR or with your computer or with your phone or wherever you are, whatever you are, you can log in. And then there's going to be hundreds and thousands of robots distributed around the world that you can log into, various different types of robots. And Digit is one of the types of of robot that they envision, although, you know, certainly a lot of the ones they're using now are wheeled machines. Log into a robot and go take a hike in the woods with your family in Japan, you know, or in China, or in Europe, or wherever you may be in the world. You can log in remotely and go with people and be with people and physically interact with things. I think it's quite possible that that's going to be a surprisingly near-term application. I think we can do basically add a control layer to this Zoom interaction that we're having, and have much better telepresence than we have right now. I've got a beam robot, by the way, in my laboratory, and the thing that drives me just nuts about it is I get stuck on an extension cord and I can't go over it. I can't deal with stairs. I can't push an elevator button. I can't go over a door threshold, and it's very slow. So having a robot that can actually go where people go may be the thing that just really allows the telepresence to take off.
All right. Okay. So I'm going to finish with, if you have time, with two, and they are the last ones, technical questions. One is the how can the robot, I guess, Digit, can sense the weight of the boxes, and what is the maximum weight that they can lift?
Okay, it can lift about 30 kilograms.
Okay.
And it's sort of sized around OSHA requirements. You know, what would you normally need to do, and how big of boxes and packages do people normally lift? And how it detects it is very much the force control. You know, you pick it up and you apply a certain amount of torque, and does it go up or does it go down? And very quickly you can dial into how heavy that package is. Same as a person does. I mean, you pick something up, and if it's a lot lighter than you expected or a lot heavier than expected, sometimes it can be a surprise. Sometimes you need to adjust to it. So early on in our applications, we would say, you know, this QR code on the package, or if it's a tote, there's a, you know, an identification on the side. We should know exactly how heavy it is and exactly the dimensions of the robot, and go into it with that expectation, just like a person does, but without having to have a world model, just connecting to the database that tells us how big or how heavy that package is. But then it's just about having the actuators be very force sensitive, and again, force control of the world with very transparent actuation, and not doing things with position trajectories.
All right. Okay. And the last question is from Xiaofeng, and I think it's a little bit general. It's about how balance control is working in unstructured environments. For example, when you climb stairs.
Okay, so that's that hierarchy of control. You know, you need to place your foot, but if you place your foot up higher, that's of course different from placing your foot down. So the planner needs to take that into account and basically be planning ahead for where's the physics going to go when I place my foot with this dynamical system that I understand. You kind of know what the dynamical system will do, and you have to plan ahead and predict what it's going to do. And there's a lot of ideas we've got about, you know, some of these are hard to simulate forward and be efficient about it. So can we learn this model in a much more compact representation that is differentiable, that actually allows us to be looking ahead at a thousand different things per second that we're going to explore to do planners like this. So you are not saying, I want to place my foot here, I'm going to follow this foot trajectory to place it here. You are instead saying, I want to place my foot there. I have a set of physics that I'm working through. If I give it a certain energy that I'm going to add, and a certain how much push off it's going to be, and I swing my leg, where am I going to end up? You know, check through that a whole bunch of times to dial in on what inputs to the dynamical system is going to get your foot. So that's what I mean about the control hierarchy and about integrating the dynamics with the planner.
All right, great. I think this concludes the questions as far as I see. And thanks a lot for staying a bit more time than I expected for the questions, but apparently we had several, and that's great.
Yeah, absolutely. I'm very happy to have questions and engagement. This was great.
Yeah.
So thank you everybody for coming.
Actually, we don't get that many questions in physical ICRA, so I hope we will manage at some point to do so. Thanks a lot, and sorry, I mean, we had some technical issues with the YouTube link, but I promise that it will be uploaded afterwards for people to watch it, other than those that were with us in Zoom. Okay, so tomorrow we have another talk with Francesco Ferro for those that are interested. I think it's in the morning, 9 a.m. UTC. All right. Okay. Thanks a lot, Jonathan. Thanks a lot, everybody, for attending, and thanks for the questions. Okay.
Excellent.
Good day. Bye bye.